Every promise this course has made comes due today. The last lesson left you holding a loaded instruction. To explore a graph, keep a frontier, and the container you choose is the traversal. So let's fire it. Here is the claim, stated as boldly as I can make it. Breadth-first search and depth-first search, the two most famous graph algorithms in the world, are the same algorithm. Watch. Keep a collection of vertices you've discovered but not yet explored. That collection is the frontier. Put the starting vertex in, then loop. Take one vertex out. Visit it. Ask for its neighbors. The order degree question the adjacency list made cheap. Add every neighbor you haven't seen before. Repeat until the frontier is empty. That's it. That is both of them in full. The only decision left, the only one, is which vertex comes out when you reach into the frontier. Make it a queue, first in, first out, and the loop explores in rings, nearest first, breadth-first search. Make it a stack, last in, first out, and the loop dives down one path until it dead ends, then backs up, depth-first search. One loop, two containers. The rest of the lesson is watching that single decision change everything. First, the setup, and the one safety mechanism everything depends on. Same 6 people as last lesson: Ava, Ben, Cleo, Dev, Ina, Finn. But switch graphs, not who follows whom, who is friends with whom. Mutual, undirected. Every edge points both ways. 6 friendships: Ava and Ben, Ava and Cleo, Ben and Dev, Cleo and Dev, Dev and Ina, Ina and Finn. And look at the first 4 edges together. Ava to Ben, Ben to Dev, Dev to Cleo, Cleo back to Ava. A cycle. Last lesson called cycles harmless in a social graph. For a traversal, they're a trap. Watch the naive walk fall in. Start at Ava. Go to Ben. Ben's neighbors include Ava, so back to Ava. Ava's neighbors include Ben. Ben again. Forever. Even one undirected edge is a two-way street, and a walk with no memory just paces it. A tree never had this problem. One parent each, no road back. Which is why Lesson 13's traversals needed no protection. A graph offers roads back everywhere, so the loop gets a memory, a visited set. Before adding a vertex to the frontier, check the set. Already in there? Skip it. Otherwise, mark it and carry on. And that set has to answer, have I seen this? Fast, millions of times. Which is exactly the job description of a hash set. Lesson 12. The first hero of this course back for the finale, doing the one thing it has always done. Membership, in order 1. Now run the real thing. The frontier is a query. Start at Ava. Q holds Ava, nothing else, and Ava is marked. Take from the front. Ava. Her neighbors, Ben and Cleo, neither seen before, mark both, and they join the back of the line. Q. Ben, then Cleo. Take Ben. His neighbors. Ava, seen, skip. Dev, new. Mark him, back of the line. Q. Cleo, Dev. Take Cleo. Her neighbors. Ava, seen, and Dev. Dev is the moment the visited set earns its keep. We just reached him a second time around the other side of the cycle, and the set says, already discovered. Skip. No double visit. No infinite loop. The trap from last scene, disarmed. Q. Just Dev. Take Dev. Ben and Cleo, seen. Ina, new. In she goes. Take Ina. Dev, seen. Finn, new. Take Finn. Nothing new. The queue is empty, and every vertex has been visited exactly once. Final order. Ava, Ben, Cleo, Dev, Ina, Finn. Hold that order on screen. It is not random, and it is not just everything once. That order has a structure, and the structure is the entire reason this version gets its own name. Look at the order again, but tag each vertex with its distance from Ava, counted in hops. Ava, 0 hops. Ben and Cleo, 1 hop each. Dev, 2. Ina, 3. Finn, 4. Now read the visit order. 0, 1, 1, 2, 3, 4. The queue visited them in exactly distance order, like a stone dropped at Ava and the ripple expanding outward, one ring at a time. And that's not luck. It's the queue's discipline doing the work. Everything at distance 1 entered the line before anything at distance 2 could even be discovered, because the only way to find a ring 2 vertex is through a ring 1 vertex. First in, first out becomes near before far. Always, which buys you the single most useful guarantee in Graphland. The first time breadth first search reaches a vertex, it has found a shortest path to it. Not a path, a shortest one, fewest possible hops. The ripple cannot arrive at Finn in ring 4 if some 3-hop route existed, because the ring 3 wave would have caught him first. So breadth first search doesn't just visit everything, it computes distances, for free, as a side effect of the container. Knowing Finn is 4 hops away is half the prize. Usually you want the route itself. And the loop is already touching everything it needs. It just has to take notes. One extra move. The moment you discover a vertex, write down who discovered it. The parent. In our run, Ben was discovered by Ava. Cleo by Ava. Dev by Ben, Ina by Dev, Finn by Ina. 5 notes, 1 per discovery. That's the entire cost. Now reconstruct. You want the path to Finn? Start at Finn and read the trail backwards. Finn was found by Ina, Ina by Dev, Dev by Ben, Ben by Ava. Reverse it. Ava, Ben, Dev, Ina, Finn. 4 hops, and the last scene proved no shorter route can exist. This is path reconstruction by parent pointers, and it is not a toy trick. Every time a mapping app draws your route, every time a network tool traces how 2 machines connect, somewhere underneath, something walked a breadcrumb trail backwards from the destination. The breadcrumbs were dropped during the search, at no extra charge. Now the experiment this course has been promising since lesson 13. Same graph, same start, same loop, same visited set, same neighbors question. One change. The frontier is a stack. Last in, first out. Take Ava, mark and stash her neighbors Ben and Cleo. Now reach in, and out comes the newest thing, Ben. His new neighbor Dev gets marked and pushed. And here is the whole personality change in one move. The queue would serve Cleo next. She's been waiting longest. The stack does not care. The stack pops Dev, the newest discovery, and commits to the path it's on. Dev's neighbors? Ben, seen. Cleo, already discovered, waiting in the stack, skip. Enna, new, push. Pop Enna, push Finn, pop Finn, nothing new down here, dead end. So the stack backs up. That's what popping the older entries is. Backtracking, returning to the last junction with an unexplored branch. Pop Cleo, her neighbors are all seen, and we're done. Final order: Ava, Ben, Dev, Enna, Finn, and Cleo last. Read what just happened. The walk went 4 levels down, all the way to the bottom of the graph before visiting Cleo, who lives 1 hop from the start. The ripple is gone. This is a spelunker with 1 rope. Follow the passage to its end, and only when it dead ends, climb back to the last fork and try the other way. Put the two journeys side by side. The queue's order, Ava, bin, Clio, dev, inna, fin. The stacks, Ava, bin, dev, inna, fin, Clio. Same 6 vertices, each visited exactly once in both runs. The same neighbors question asked the whole way. But one walk moved like a ripple, ring by ring outward, and the other like a spelunker, straight down and back up. And in the code, the difference is which end of the container you take from, the oldest discovery or the newest. That is the only line that changes. And here's the loop this closes. Lesson 13. On trees, you wrote level order with a queue and pre-order with a stack, watched the identical skeleton and heard the claim, the container is the traversal. Trees were the special case all along. Of the 4 tree traversals, 3 of them, pre-order, in-order, post-order, were depth first. 3 flavors of the dive, differing only in when they pause to look at a node. And level order was breadth first, the ripple. You have been running both of these algorithms since lesson 13, on graphs so polite, one parent, no cycles, that they never needed a visited set. Today, the training wheels came off. The algorithms didn't change. So when do you reach for the ripple? Whenever the question contains the word nearest or the word shortest. Open your profile on a professional network and look at the little badges. First, second, third. That label is literally the ring number. Breadth first, search outward from you through the connection graph. Second degree means discovered in ring 2, nothing more mystical than that. The people you may know box, same engine pointed sideways. Sweep ring 2, collect friends of friends who aren't friends yet. Rank them by how many ring 1 paths lead there. And the old claim that any 2 people stand 6 handshakes apart? One famous experiment in the 1960s forwarded letters through chains of acquaintances, and the ones that arrived took about 6 hops. Hedged, imperfect, endlessly debated. But that's the phrase's origin, a measured ripple. Web crawlers, same loop at planet scale. Seed pages go into the frontier. Every link is an edge. The crawl expands outward, exactly like our 6 friends did. Visited, set keeping it from chasing its own tail. Even garbage collectors. A tracing collector's mark phase starts from your live variables and traverses everything reachable from them. The textbook description uses 3 colors of vertex, and it is this traversal in spirit. Whatever the wave touches is alive. Whatever it never reaches is garbage. And now the promise from last lesson, the graph that is never stored. A maze. Cells are vertices, edges connect cells you can step between, and nobody builds the adjacency list, because given a cell, the neighbors are computable. Up, down, left, right, minus walls. So run breadth first search anyway. A queue of cells. A visited set of cells. Neighbors conjured on demand the moment the loop asks. The ripple spreads from the entrance, ring by ring through the corridors. And the first time it touches the exit, that is the shortest escape. Guaranteed. Fewest steps. The algorithm never even noticed the graph wasn't there. Word ladders. Cat to dog, 1 letter at a time. Identical move. Breadth first over words, shortest ladder, no graph in memory. But here's the honest caveat, and it's a door. Shortest today means fewest hops. Every edge costs 1. The moment edges carry weights, a roadmap, minutes per segment. Fewest hops stops, meaning fastest. The 3-hop highway beats the 2-hop dirt road. The fix? You already own it. Swap the container again. Not a queue, a priority queue. Lesson 15's heap always serving the cheapest route so far. That is Dijkstra's algorithm, and it's the first thing waiting in part 2. Notice why it'll be cheap to learn. The container swap you watched today is the entire trick. Back to the dive, because depth-first search has a secret identity. Lesson 9. Every function call pushes a frame, every return pops one. The call stack is a stack you don't see, so watch this function. Visit a vertex, mark it. For each unvisited neighbor, call yourself. That's the whole function. No container anywhere in sight. And it is depth-first search, because the container is the call stack. Every recursive call pushes one level deeper down a path. Every return pops back to the last junction. The explicit stack version and the recursive version are the same algorithm in different clothes. One keeps the stack in a variable, one borrows the runtimes. Run it on our graph and read the order. Ava, Ben, Dev, then Cleo. The recursion reached Cleo through the back of the cycle, from Dev. 3 hops. She lives 1 hop from the start. And that nails down the contrast from the ripple. Depth-first search finds a path. It never, ever promises the shortest one. One caveat before you trust it everywhere. Lesson 9 ended in a Stack Overflow, and graphs can resurrect it. A graph shaped like a million vertex chain means a million frames of recursion depth. For huge or unknown graphs, use the explicit stack. Same algorithm, ordinary memory, no short leash. So if the dive can't promise shortest paths, what is it for? First answer, reachability. Can I get there from here? And what is the full extent of everything I can touch? You have run this one with your own mouse. The paint bucket in any image editor. Click a pixel and the fill spreads to every connected pixel of the same color, stopping at the borders. That's called flood fill, and it is a graph traversal. Pixels are vertices. Touching pixels of the same color share an edge. Another graph nobody stores. Click, dive, everything reachable changes color. And notice, depth first or breadth first, either one works here because nobody asked for distances, just everything reachable. Order doesn't matter, membership does. The generalization has a name, connected components. Traverse from any vertex and you've mapped one island. Something still unvisited when you're done? Start again from there. Second island. Count the restarts and you've counted the components. It's how an editor finds distinct regions in an image. And it's how you answer questions like, if this machine goes down, which parts of the network can still reach each other?
Second answer,
Structure. Last lesson called a dependency cycle a disease. A depends on B depends on A, neither can build first. And promised the detection was a traversal question. Here it is. Run the dive over the dependency graph, but track each vertex in 3 states instead of 2. Never seen. Currently on my path, meaning the dive entered it and hasn't returned from it yet, and fully done. Now watch it catch one. A depends on B depends on C depends on A. Dive into A, on my path. Into B, on my path. Into C, on my path. C's dependency is A. Check A's state. Still on my path. The dive is standing on its own tail. Cycle, caught in the act. And the third state is what makes this precise. Meeting a done vertex is fine. 2 packages depending on one shared library is a diamond, not a loop. The library finished long ago. It's done. Pass through. Only on my current path means trouble. This check, or a cousin of it, is what cargo and npm run across your dependency graph before building. And one more gift hides in the same run. The order vertices turn done, read backwards, is a valid build order. Dependencies always first. That trick is called topological sort. It's part 2's first graph move, and you now hold every piece it's made of. What does all of this cost? Derive it once, it covers both. Every vertex enters the frontier at most once. That's the visited sets guarantee. Every vertex that comes out gets its neighbor list scanned once. And summing neighbor lists over every vertex is just every edge, examined once from each end. Total bill for either traversal, order V plus E. Each vertex once, each edge once. You cannot inspect a whole graph for less. And notice who made it possible, the adjacency list. Its order degree neighbors answer is why the sum collapses. A matrix would charge order V per vertex, order V squared for the whole walk, no matter how sparse the graph. Last lesson's storage decision became this lesson's speed. So if the bills are equal, how do you choose? Ask what the question is. Shortest, nearest, level by level. Q. Existence, structure, just visit everything. Stack. Often the recursive one, it's less code. The real tiebreaker is memory. The queue holds an entire ring of the frontier at once, and on a social graph, ring 2 can be millions wide. The stack holds one path, start to current depth, usually far leaner. Unless the graph runs deep and you're recursing, lesson 9's warning. Width or depth. Know your graph's shape, and the choice makes itself. And that is the course. Look how far this walk went. It started with a 6-minute loading screen and one question. What does a step cost? You learned to count, big O, the growth ladder, the amortized bank account. Then the machine got a vote. One step is not one step. A desk reach or a hallway commute, and the memory hierarchy decides which. With both prices in hand, you built the structures. Arrays, strings, linked lists, stacks, and queues. You learned the moves, two-pointers, binary search, recursion, divide and conquer, sorting. Then came the workhorses, the hash table, average order 1, the course's first hero. Trees, the search tree, the heap. And finally, the shape with no constraints left, the network. And the 2 traversals you ran today, the patterns every graph algorithm is built on. Here's what you actually walk away with. You can now pick up any structure, any algorithm, anything in a library's documentation or an interviewer's question, and ask the 2 questions this course installed. How does the cost grow as n grows? And how does it touch memory? Those 2 questions are the whole discipline. Everything else is detail you now know how to price. So what's left? Plenty. And that's the good news. The structures that run production databases and the patterns that close interviews, balance trees, B trees, caches that forget on purpose, the cheapest first traversal we teased today, dynamic programming, every one of them starts from something now sitting in your toolkit. That course is called DSA Patterns, and it assumes exactly what you just finished. But that's tomorrow. Today, take the win. 17 lessons ago, a loading screen took 6 minutes and you couldn't have said why. Now, you could find it, name it, price it, and fix it. That's not trivia. That's the craft. Thanks for walking it with me. See you in part 2.